Good morning. My name is Luca Ferragina, and I am a PhD student at the University of Calabria. I will present the paper I wrote with my advisor, Professor Fabrizio Angiulli, and Professor Fabio Fassetti. The paper is entitled Improving Deep Unsupervised Anomaly Detection by Exploiting Variational Autoencoder Latent Space Distribution. Let's see the plane of the presentation. In the first section, we are going to introduce the context and the instruments at the basis of our work. In the second section, we will describe the details of our algorithm, called Variational Autoencoder Out, and the reasons behind it. Finally, we will show some of the experiments we conducted in our work. The context of our work is the unsupervised anomaly detection, that consists in, given a dataset S, detecting outliers in it by assigning a score to each object. The classical use of an autoencoder in anomaly detection is based on this simple paradigm. First, the autoencoder is trained on S. Then its loss, the reconstruction error, is used as an anomaly score of the sample X. Usually, we use the mean square error as a reconstruction error. The idea is that we consider as anomalies the worst reconstructed sample in S, because since the inliers represent the majority of the data, the autoencoder is trained to better reconstruct them. Variational autoencoders are complex stochastic generative models, but in the context of anomaly detection, they are used in a way similar to the standard autoencoders. That is, first, a variational autoencoder is trained on the dataset S. Then, for the sample X, is defined the reconstruction error that we can see in this formula. These represent a generalization of the one we have seen for the standard autoencoders, and consist in a Monte Carlo estimation of the first term of the loss of the variational autoencoder. In the same way as standard autoencoder, here we are considering as anomalies the worst reconstructed examples. Although this use of variational autoencoders have improved the performances of standard autoencoder, we argue that this approach is too simplistic if a variational autoencoder is employed. To prove this sentence, we build the following experiment. We consider the mixed dataset, and since it is a multi-label dataset, we created a binary dataset composed by all the digits from the class 0 as inliers, and as outliers, 90 digits from the other classes, 10 from each class, randomly picked. Let us give some notation. We will denote with I the input space, with L the latent space, with E the reconstruction error space. In this picture, we can see the plot of the latent space. The points in blue are the inliers, and the stars in red are the outliers. In this example, we set the dimension of the latent space equal to 2 in order to visualize the latent space. In the following, we are going to better analyze the impact of these parameters. We can see that since the inliers are the majority of the data, they will be encoded as distribution similar to the standard normal. But a non-negligible fraction of inliers spread also over a more peripheral region. The outliers spread over a wide portion of the latent space, including both boundary regions and the central region. The position of an outlier will depend on its similarities to the normal class. Because of these reasons, neither the location of the distribution in the latent space nor the degree of overlapping alone are sufficient to separate inliers from outliers. To overcome these issues, We consider a novel feature space that we call F, and it is composed by the Cartesian product of the latent space and the reconstruction error space. In this picture, we can see the plot of this novel feature space. That is a three-dimensional space, since we added one dimension to the latent space. We can see that most of the outliers have a low reconstruction error. Indeed, there are a lot of red stars at low levels of the vertical axis. This means that the reconstruction error alone is not sufficient to guarantee a good separation between inliers and outliers. Moreover, outliers tend to lie in the sparsest region of F. This happens because, even when its reconstruction error is low, an outlier tends to have a reconstruction error larger than that of the inliers that are close to it in the latent space. All these facts tend to move away the outliers from the inliers in the augmented space. Based on these remarks, we build our algorithm. As per step, we train a variational autoencoder on the dataset in which we want to find anomalies. Then we define the transformed dataset ZS, that is the dataset S, mapped into the feature space F. After that, we consider the dataset ZS bar, obtained from ZS by normalizing each feature according to its mean and its standard deviation. Standardization is needed to handle non-homogeneous feature. Finally, we define the variational autoencoder out anomaly score of the point xi in S as the k-nearest neighbor estimate of the density of zxi bar in zs bar. In this picture, we can see the plot of the latent space together with the variational autoencoder out anomaly score. We can see that here we have a good separation in terms of this score. This leads to an improvement in terms of outlier detection performances. In this picture, we can see the ROC curve of both our algorithm in red and reconstruction error in blue. The area under curve is 0.90 for reconstruction error and 0.99 for our algorithm. We expanded the previous experiment by considering some multi-label dataset and by building different binary datasets from each of them in the same way as we did before. That is, for each class, we created a novel dataset having as inliers all the examples of the considered class and as outliers a quantity S of randomly picked example from each class. Usually we set S equal to 10 or 100. The contamination of this dataset, that is the number of outliers, is equal to S times m minus 1, where m denotes the number of classes. In this experiment, we investigate the effect of the increasing of the latent space dimension d on the performances of both our algorithm and the reconstruction error. In the following, we show the results obtained with the MNIST dataset with k equal to 15 and s equal to 10. In this slide, each plot is relative to one of the datasets obtained as we have described before. On the horizontal axis, we have the dimension of the latent space, and on the vertical axis, we have the area under curve. The red line is for our algorithm, and the blue line is for reconstruction error. These results are obtained after 10 runs for each dataset, and so we report the mean and the standard deviation of the area under curve or both the algorithms. We can see that in many cases our algorithm improves over reconstruction error, and often this improvement is sensible. The accuracy of variational autoencoder, out, is positively affected by the increasing of the latent space dimension, while this does not happen for the standard variational autoencoder approach. This happens because lower dimension constrain distributions within the latent space to overlap more, thus worsening separation. From these experiments, we conclude that the good choice for the latent space dimension is D between 16 and 32. The performances of our algorithm depend on the choice of the parameter k relative to the k nearest neighbor we perform on F. In order to investigate the impact of this parameter, we build the following experiment. We consider log space value k in the interval to 1024 and determine the area under curve of our algorithm on the MNIST dataset for s equal to 10 and s equal to 100. We fix the latent space dimension to 32, and to better understand the effect of k, we consider the value k divided by c, that is called normalized neighborhood, and that is it is k normalized by the absolute contamination. This plot is relative to the dataset obtained from NIST by considering the class 0 as outliers. On the horizontal axis, we have the normalized neighborhood, k divided by c, and on the vertical axis, we have the area under curve. The red line is relative to the dataset with s equal to 100. The blue is relative to the dataset with s equal to 10. In the legend, there are the relative performance of the reconstruction error. In this picture, we can see the plots relative to the datasets obtained with all the other digits as outliers. We can see that for a wide range of values of the parameter k, the area under curve of variational autoencoder out is sensibly larger than that of the reconstruction error. And although our algorithm requires an additional parameter, k, with respect to the standard variational autoencoder approach, the selection of the right value for k is not critical, since an improvement is almost always guaranteed. The optimal value for normalized neighborhood, k divided by c, appears to be located within the interval 0.1, 1. Because of this, we recommend to use t equal to n divided by 3, where n is the user-specified expected absolute contamination, or to return n anomalies, where k is user-specified, with n between 3 times k and 5 times k. We conclude the presentation with a list of the direction in which we want to expand our work in the future. First, we want to investigate other measure of density in F instead of the k nearest neighbor. And more generally, we want to define new rules for combining latent space and reconstruction error for a variational autoencoder. Then we will want to extend our approach to supervised and semi-supervised settings and enlarge the experiments to datasets of various types. And finally, we want to compare our approach also to algorithms that are not based on neural network. With this, I conclude my presentation. Thank you for your attention.